this part. So anyway, take it away, Dr. Parkinson. There he is.
Hey, thanks a lot, Lynn. Thank you very much for the introduction and the invitation to come and talk to you. It's a real pleasure and honor. And yes, it has been quite a long time. I don't want to say how long. I don't want to reveal my age, but let's see. I'm going to try to share my screen and then start my slides. Okay. Share. And then I'll start playing. So does that look okay?
Yes.
See it fine? Okay. All right. So today I'm going to talk to you a little bit about how we can use the space station to study pulsars. And in particular, I'm going to talk about studying gamma ray pulsars, which is the main area, the subset of pulsars.
Sorry? Yes, where is he?
The macro.
Sorry, I'll mute the person. Go ahead.
Oh, okay. Sorry. So this is, by the way, this is the experiment that I'll talk a little bit about. It's called NICER, and I will discuss how it's located on the space station. Indeed. So what you see in the background there, the yellow, is actually the solar panel for the space station. Before I do that, though, I do want to give a little bit of context. I'm not sure how familiar you all are with pulsars and with gamma rays and so on. So I will just give a quick summary of what a pulsar is. A pulsar is a highly magnetized rotating neutron star. So there's a lot of words there. So neutron star is probably one of the most exotic objects in the universe. They were predicted all the way back in the 1930s by these two fellows in a paper. However, the discovery of a neutron star wasn't actually in practice till the 1960s, late 60s. That was when the first pulsar was discovered. And so a pulsar is a particular type of neutron star that is highly magnetized and it's spinning, it's rotating. So when I say highly magnetized, it means it has a very, very strong magnetic field. So to give you a little bit of an idea of how strong we're talking about, you probably all know that you can think of the Earth as a magnet. The Earth has a magnetic field, and the strength of that magnetic field is about half a Gauss. Gauss is just the unit we use, one of the units for magnetic field. Now, the sun is also magnetized, and the magnetic field of the sun is about twice that of the Earth, so it's not a huge amount. And to give you a sense of how strong these magnets are, you probably all played with a bar magnet, maybe at some point in your life. So these bar magnets that you see there, that's about 100 Gauss. Okay, so now we're getting into sort of slightly stronger fields. Now, the very strongest magnetic field ever generated on Earth, the record is by this facility in Florida. It's called the National High Magnetic Field Laboratory. And this is about 1 million times stronger than the magnetic field of the Earth. Okay, it's 500,000 Gauss. So that's a huge, very, very strong magnetic field. Okay, so a neutron star, a pulsar in particular, can have a magnetic field that is about 1 billion times that. So hopefully that gives you a sense of just how strongly magnetized these objects are. So the other thing I said, it's highly magnetized, it's also rotating. And the other thing that I did not mention here is how massive it is. So a neutron star is about as massive as the sun. On the other hand, it's very, very compact. It's only about the size of some typical city. So it has a huge density, huge magnetic field, and it's spinning very fast. So the combination of all these things make them extremely interesting objects to study. Now, as it turns out, these objects emit a lot of radiation in the gamma rays. And so they've been studied in gamma ray astronomy for a few decades now. However, until quite recently, this slide here that was created some years back basically is sort of a summary of our view of gamma ray pulsars, that is pulsars that emitted gamma rays. So you can see that until about 20 years ago, there were only about 7 of these gamma ray pulsars. Now, what this slide shows is that pulsars can emit radiation in various different bands. So they can emit, if you look on the different colors, so the yellow, the bottom row of that figure shows the gamma ray emission. You can see that you have these pulses, and you see that there's different bands, X-ray, and you see pulses, optical, and radio. And now, until about 20 years ago, there was this mystery about this one pulsar called Geminga that had gamma ray, a very bright gamma ray peak, but you can see there's no radio pulse, and you can see it's the only one that had no radio pulse. And so I'm going to tell you about a mission that was launched to try to answer a number of mysteries, but among them was why is it that you have some pulsars, in particular this one pulsar that doesn't emit radio waves? And the other mystery that that was out there was that this experiment, this gamma ray telescope, which was known as EGRID, detected many, many gamma ray sources. A lot of them were so-called unidentified. People didn't know what they were. And so the combination of these two mysteries meant that some people speculated that maybe some of these unidentified sources were actually what we call radio quiet pulsars, radio quiet gamma ray pulsars. And so in 2008, June 2008, we launched the Fermi Gamma Ray Space Telescope. This was, so last year we had the 15th anniversary. This telescope was launched from Florida on a Delta II rocket, and it's been operating for 15 years, but it's actually more than 15 years, but it actually keeps operating fine. It doesn't have any sort of expendables, and so it can keep going hopefully for a very long time. It has 2 main experiments on it. One of them is known as the Large Area Telescope, or LAT, and the other one is called the Gamma Ray Burst Monitor. Now, I'm only going to talk about the Large Area Telescope today. Remember I said that before the launch of Fermi, we knew about 7 gamma ray pulsars. Well, since the launch of Fermi, this graph here, if you look at the black line, tells you how many gamma ray pulsars we know. And we've crossed the threshold of 300. So you can see the big impact that Fermi has had in the field of gamma ray pulsars. Now, the different colored lines, I won't go into all the details, but basically there's various ways in which we can detect these gamma ray pulsars. One of them is what we call blind searches. So this is searches using only gamma ray data. It's blind because we don't use information from other telescopes. And so this is the first time that we were able to do this with Fermi. All previous gamma ray pulsars that were detected using information from other telescopes, primarily radio telescopes. Now, I'll also point out, if you see around the year 2011, end of 2011, there's a pulsar there called J2021, that's just for short, and it says mode shift. And I'll be talking a little bit about that one pulsar in particular. So I sort of got ahead of myself a little bit, but I mentioned that we knew about this one interesting pulsar before the launch of Fermi called Geminga, but it was the only one of its kind. So soon after launch, we were able to discover a lot of different other pulsars like Geminga using only the gamma ray data. And so this was one of the papers we put out early on with the first 16 of these. And the interesting thing about this is that after we discovered these in gamma rays, we wanted to make sure that these were indeed radio quiet. And so by the way, one of these 16 is the one that I will discuss a little bit in more detail. It has this number. So pulsars are named by their coordinates. There's, just like on Earth, we have latitude and longitude. On the sky, we use coordinates known as right ascension and declination. So those numbers just represent the coordinates where the pulsar is located. And so you can see this was the what we call the pulse profile. So what this shows is the x-axis you can think of as time. It's basically 2 rotations of a pulsar, and then the y-axis is just photons that we're accumulating, in particular gamma rays that we're accumulating. And so what this tells you is that the neutron star is spinning, and as it spins, it spits out photons, and then we put them all in a bucket, and then we sort them by time, and then we see this pulse. So, of course, when we discovered it, we don't necessarily know whether it's radio quiet. So one of the things we did was enlist the help of the radio telescopes, the biggest radio telescopes on Earth, and a large number of them collaborated with us to observe these telescopes. Here you see in this graph, and the picture shows actually currently the largest single dish radio telescope. So it's 500 meters across. Okay, so compare that to some of the other, these are all quite famous telescopes. Arecibo, unfortunately, used to be the largest single dish radio telescope. That no longer exists. It was damaged, and it's not going to be rebuilt. But you can see that this telescope in China, FAST, is an enormous radio telescope. So that gives you an idea of how sensitive this telescope might be. And we have been collaborating with them. This is the cover of an article that we published when we discovered a new pulsar with them. However, going back to the pulsar that I mentioned, the Gamma Cygni, when we use this fast radio telescope, we observed it for quite some time, and there's no sign of a radio signal. So it is indeed another radio quiet pulsar, just like Domingo. So this, by the way, is what we call the sky map, showing the gamma rays detected by Fermi over the course of more than 10 years. So what you see in this map, which is in what we call galactic coordinates. So earlier I mentioned right ascension and declination, but there's another way in which you can represent the coordinates, which is with the galaxy showing up on the plane. So if you think of us being sort of inside this galaxy, there's a plane. So if you looked from above, we would see sort of the center of the galaxy and so on. But you can imagine this is the galactic, what we call the galactic plane. And of course, the galactic plane has a lot of activity. It has a lot of gas. It has a lot of stars, and it has a lot of pulsars. So I'm zooming in on this region of the sky. This is a region known as the Cygnus region. And you can see I've sort of labeled a lot of these pulsars. So, of course, I haven't shown you the egret sky map, but just to give you an idea of how much better the resolution and the map is with the Fermi telescope, the previous mission, egret, in its entire lifetime, collected about 1.5 million photons. It detected about 1.5 million photons. So with Fermi, we've already detected more than 1.5 billion. So that's more than 1,000 times more. And so what we can do, of course, with this is much more detailed. Now, I'm going to talk about actually two pulsars that we've been looking at and studying with NICER. I mentioned Gamma Cygni, so that one is the brightest one you see there. If you see the sort of top left, PSRJ 2021 plus 4026. So you can see that it's very bright. And the one just down to the lower right is not quite so bright. It's quite faint, in fact, PSRJ 2022 plus 3842. But that's another very interesting pulsar. So these two pulsars, I will say a little bit more about, because we're currently conducting joint studies with Fermi and NICER. So I mentioned that we used this big radio telescope, FAST, to try to see whether we can detect any radio emission, and we can't. It's radio quiet. So that means that we can't use radio telescopes to study this pulsar. On the other hand, if you look at it in the X-rays, X-ray telescopes have much better angular resolution, and so you can pinpoint sources much more precisely. And so we did that with a telescope called Chandra, and we identified what's known as the X-ray counterpart. So the object that is emitting X-rays also at the location of this pulsar. And so that object there, source number 20 in this image, is an X-ray emitting object. So we may not be able to study it in radio, but maybe we can study it in X-rays. And so that's exactly what we did. So we started by obtaining observations with another telescope, which has what we call larger effective areas. So it collects more photons than Chandra. So this telescope in particular is known as XMM Newton. It's a joint European Space Agency and NASA telescope. And so when we observed this pulsar with X-rays, you can see that this black curve, so the red curve is the one that I've shown you before, is the gamma ray pulse profile. You can see it has the two peaks there as it rotates. It turns out that in X-rays, you also see a pulse profile. It's slightly different. So you can see that the red one has two peaks, whereas the black one has one peak. And there's a few other things that are different about this. Of course, we're observing in very, very different energy bands. Okay, the gamma rays are much, much higher energy. And so we're probably looking at very different locations of this object. But nevertheless, what is the same in both cases is the timing signature. So both of them, and this is basically represented by the x-axis. When I say phase, you basically have two rotations of the pulsar. And so as they rotate, they emit both X-rays and gamma rays. So one other thing that is extremely interesting and unique about this pulsar and gamma Cygni is that unlike every other young gamma ray pulsar that we've seen, this pulsar isn't just a steady gamma ray source. So gamma ray pulsars are known to be, on long time scales, are known to be quite steady. So the number of photons that you get basically every day is pretty constant, okay? Now, what this pulsar showed in 2011 is a dip in the flux, a dip in the number of photons that we get, quite significant, by about 20%. You see that it sort of suddenly went, oof, the flux lowered. And at the same time as this happened, what we saw was a change in the way that it's spinning. The frequency spin down rate. The spin down is what most pulsars do. Most pulsars, these young pulsars sort of are slowly spinning down as they lose energy. So this rate increased. So this variability, this phenomenon, is completely unique in this pulsar, and we haven't seen it in any others. And so what we tried to do is see whether there's any difference between the X-rays and the gamma rays when you have this shift. And so using XMM for a very long observation, but just two very specific points in time, what we observed actually a couple of years ago, this was published last year, was that in fact, the phase of these two oscillations, the gamma ray and the X-ray, actually shifts. And so this is actually something quite hard to explain, quite tricky. Now, we have one of our colleagues, a theorist known as Alice Harding, who studies these systems with simulations, has speculated what might be going on. This is not an extremely detailed model, but the idea is that we have two types of radiation coming out. One of them, a slightly lower energy that we think may be coming from closer to the surface of the neutron star. And then the gamma ray is much higher energy, that come from much further out. And so perhaps what's going on when you have this episode is that there's some rearrangement of the field lines. And so we have some complicated phenomenon going on. And in order to be able to really understand and see whether this explains what went on, the problem is that we can't just rely on one incident. And so luckily for us, this system seems to undergo this variability phenomenon more than once. It's done it already twice. It seems to maybe be doing it a third time. So this is a long. You can see this is more than 10 years of data, and you can see that it sort of does this on a 6 to 7 year timescale. So we've been up now for about 16 years. So we maybe will get to see it the third time. So this is where NICER comes in. So why is NICER a perfect instrument to be looking at this? Well, I mentioned XMM Newton a couple of times. This is this European Space Agency and NASA telescope. Well, that figure that you see, that plot, is what we call the effective area of the instrument in the energy range that we're especially interested in. And what you can see is that NICER in this specific energy range is actually has a much larger effective area. And so it's very well suited exactly in the energy range that we're interested in. The other thing is that because we're looking at these timing signals, we need very, very precise timing resolution. And so NICER has much, much better timing resolution. That's better than 300 nanoseconds. So a nanosecond is 10 to the minus 9 seconds. So you can imagine there's a billion nanoseconds in a second. So NICER was launched in 2017, which is already 7 years ago, I guess, almost. But it's still going strong. It's a set of 56 X-ray, what we call concentrator telescopes, and with silicon drift detectors. It has a fairly large field of view for X-rays, and the main thing that is very good about it is that it can carry out many monitoring observations. And so this is exactly what we're doing. By the way, I'm going to try to play this movie so you can see. Let's see if it works. So this is sort of a movie showing the operation of NICER. You can see it. The panel comes in. So it really needs to know exactly what's going on, make sure that it's not pointing towards the panel. So you can see the 56 detectors there. And so you basically can get observations of about 1 or 2 hours. And then you have to sort of make sure that you're not staring at the panel. But now, one of the big advantages of being on the space station is that power is normally a big problem for satellites. You have limited resources. However, on the space station, you have basically unlimited power. Also, you can have astronauts fix things if they need to move something, or you can make adjustments to the instrument. So there's a lot of advantages to being on the space station. By the way, you might have noticed there was another instrument there right next to it called AMS, the alpha magnetic spectrometers. So that's another famous instrument, but I won't go into that. But let's see. Okay, hang on. Let me stop this. So I noticed there's a couple of chat. Let me just see quickly. I'm trying to see the chat, but I don't.
I can read the chat. I just noted that
Okay, sure.
2008, when you mentioned a launch, was when most of our students who are calling in today were probably born.
Oh, wow. Yes, that's great. Nice.
And Lynn made a comment about something being very accurate, but I'm not quite sure what she was referring to.
Oh, okay. Let me quickly see. I know that we're running short on time. So yeah, this is sort of a close up of the diagram of what NICER looks like. So you have about 56 independent X-ray detectors, and this is just to show you. So these are like a set of observations of this pulsar that I'm talking about, gamma signaling. And you can see that we can see the pulsation quite clearly there. So this is work that's still in progress. And by the way, if you want to get more details about NICER, there's a web page called HESARC, has a lot of details about analysis that you can literally grab data from there, and I highly recommend browsing it. Let me quickly just discuss this second pulsar that I mentioned that we're working on. So the reason this pulsar is quite interesting for a number of reasons. It's one of the most energetic known pulsars. It's extremely, extremely energetic. And it was actually very difficult. It was discovered in X-rays, and it's very faint in radio. It's not exactly radio quiet, but it's very faint. So again, this is one of these pulsars that is very good to observe in X-rays. And actually, even though you see that it's emitting gamma rays, because it's so young and so energetic, this was actually a pulsar that was very, very difficult to obtain the gamma ray pulsations from. So a student here at Santa Cruz worked very hard to use NICER observations to obtain what we call a timing model. So if you obtain a lot of precise timing observations, you can then use the timing information from NICER to then what we call fold the gamma ray data. Now, what's interesting is that these two plots, the one on the left is the NICER data, and the one on the right is the gamma ray data. But the y-axis is time, basically. The difference is that the y-axis in the lab is basically going for quite a bit longer. So if you get enough time X-ray timing observations, you can then, if you're lucky, extend the timing model beyond this. Now, this is another reason why this pulsar is very interesting, is that because it's so young and because of where it emits the gamma rays, we think that it's also sort of a pulsar that is unlike most of the other gamma ray pulsars that Fermi is detecting, and may point to a population of sort of lower energy gamma ray pulsars that may be hiding there. And so we hope that NICER and other X-ray telescopes can help us find it. So this, what this plot shows is how over the course of these this time, so this is the X coordinate is in what we call modified Julian days, if you like. So this is more than 4,000 days, so 3 years. You can see that the pulsar is spinning down. And so we were able to do that thanks to NICER. And there's 2 episodes where the timing is discontinuous. That's because this type of pulsar often has these sort of jumpy behaviors. And so by doing that, we were able to obtain this gamma ray, what we call the spectrum, and then to be able to fit it with a model which tells us and helps us better understand the sort of the emission process that we think is at play. And so, as I say, this might be sort of a pulsar that is pointing towards other very similar pulsars that we haven't been able to detect yet. So with that, I'm just going to leave my summary slide here, and I just want to highlight the fact that using NICER to obtain sort of to carry out joint studies with Fermi has been extremely productive, and we hope that it can continue for many years, because as I've mentioned, a couple of these pulsars, basically there's no other channel that you can study them. You can't use radio telescopes as you can with most of the other thousands of pulsars, and so it's extremely useful to be able to study the signals from these different wave bands combined, and also to carry out these monitoring observations. So hopefully we'll continue to work on this, and the nice thing is that the data continues to accumulate. And so if you're a student who's interested in working on these data, it's definitely something that you would be able to do. Also, there's a lot of material online on the HESARC webpage that I mentioned to sort of provide guidance on how to actually carry out analysis with NICER, like most NASA missions, in fact. So I think that I definitely encourage you, if you're interested in pursuing this further, it's a quite an exciting project. So with that, I'll open up to questions.
Thank you. That was really interesting. We actually have a question in the chat from Willow, which you might be able to see now that you're not sharing. But I could read it to you.
Oh, let me see.
It says, are there any patterns on where the pulsar's magnetic poles are in relation to their rotational poles? And do the differences between the two affect the radiation we pick up from them?
Yeah, that's a very good question, actually. Yeah, so it takes a lot of modeling to understand this, but definitely the angle between the rotation and magnetic field is a very relevant parameter to try to predict. And what you get is some people who work on simulations of these systems, you can basically come out with different pulse profiles. Some of these can explain why, for instance, some of them might have 2 peaks instead of 1 peak. It's not, it's not a completely obvious one-to-one correspondence, but definitely it's one of the parameters that is used as an input to sort of try to understand what the signal is we're seeing. Because of course, when we look at these, you're sort of projecting on just one plane, and so you have to sort of imagine what's going on and try to model that. Yeah.
Any other questions? You can either raise your hand or write something in the chat.
We have a very quiet and small group today.
Pablo, is it okay with you if I post the recording of your talk on our website?
I think that's fine. Yeah, sure.
Awesome.